Okay, so we are continuing with from our last topic, Wiener filtering discussion. So what we have said last time. So let's assume that I have process x of n. This is a random process. And one of its sample is, let's say, x n minus k. So these samples are linearly combined, and I get an estimate for another process, which is the desired process's estimate. So the issue is, in Wiener filtering, how do you set this linear combination coefficients? Okay. Now this is the case that we have studied previously. Well, this is the FIR case. FIR case. Okay. Now the issue is the following. How am I going to select this linear combination coefficients? Well, we define this criteria, desired process minus estimate of this desired process at the same time instant. Okay? Then their difference will be the error, and I would like to minimize the mean square error. So to minimize the mean square error, we have previously studied this problem. Let me assume that this is my desired random variable, and this is the observation vector x. Then I can express this linear combination as an inner product, as you see. And then I can apply my linear MMSE result, which is for all linear combinations, the solution for this problem, which we call, this is also called normal equations. Normal equations is in this form. So what is this? Autocorrelation matrix of the observation vector and the cross correlation of observations and the desired quantity, x and y. Okay? So x is a vector, y is a scalar over here. So I'm focusing on the real valued case, okay, for the sake of simplicity for now, even though we have studied the complex valued case also. So you can see this part is expected value of x and y. So of course both of them are real valued. I can write it like this, y and x. Because of this trivial calculation, the second argument can be x and so on. So for the complex valued case, actually this matters, because this representation shows us that the second argument is conjugated. Okay? So if it is real, then conjugation is not doing anything. Then we have such an equality. Now if I apply this result for the same x vector, I have again Rx is Rx. Then on the right hand side, x vector is the observation vector, y is the desired process. So over here I have the cross correlation of desired process and sample and my observation vector samples. Okay. So this is exactly the same thing that we have studied before, but right now we are calling this Wiener filtering because this is nothing but, as you can see, this is the convolution of W of n with x of n. Okay, where W of n is, it's a FIR filter. So this is, let's say, W0, W1, it goes up to here, let's say up to WP minus 1. So the rest is all 0. So this is n, before it is 0. So this is the convolution relation for a p-tap. So this is 0, this is 1. So I have dots up to p, okay? P minus 1, sorry. So it's a p-tap FIR filter. It's a causal filter. So this is the reason that we are calling this, not a linear MMSE estimation, but some kind of a filter application, and this is called Wiener filtering. Okay, so this is revisiting the previous topics, but this is the basis of everything that we will say, let's say, in the next hour or so. Okay, so let me write categorization of let's say signal processing operations. Let me say a categorization because it's not very, specific. So number one, this is filtering. So the word filtering. So this assumes a linear combination of input samples up to let's say, not utilizing the input samples in the future. Okay, not utilizing. So what's the meaning of this? It's like a causal operation. Causal, let's say, operation. Okay. So when we say filtering, in general, we understand such an operation. When we say we have a filter implemented, it's exactly something like this. So this is the FIR case. So you see that this impulse response, W of n, over here. So this is a causal impulse response. So as you see, to produce this n sample at the output, I'm using x of n minus 1, and so on. But I'm not using x of n plus 1. I'm not using any sample in the future. Okay. So this is what we understand from the word filtering. Now the second one is smoothing. So this is again a linear combination of input samples which are both in the history, let's say in the past, and future of current sample. So this means that this can be, it's an anti-causal operation. So you can say that, how can you implement an anti-causal operation? But in practice, for example, in image processing and so on, you see the whole image, isn't it? You are not seeing these image pixels in a sequence. But in, let's say, in a telephony application, all of these incoming information is flowing in, and you are filtering that information, the information flowing in. And you don't want to have any latency in the system, you don't want to have the delay in the system. So you are just implementing a causal filtering of all of the samples, the current sample and the samples in the history. Okay. But for the smoothing application, sometimes you can see, the samples which have indexes higher than the current sample. So why not combine them if I can reduce, let's say, mean square error? Okay, if I can reduce this mean square error. So this is called the smoothing operation. So what is the difference? Well, the difference is this. Now so this is just an example. My W of n is, let's say I have a 5-tap filter. So I have a W0, I have a W1, I have a W2, well, let's say something like this, W minus 1 and W minus 2. So the rest is all equal to 0. Now the question is, so my impulse responses, as you see, an anti-causal sequence. So what do I mean by this? Now d of n is, d head of n is, so let me write this vector. W minus 2, W minus 1, W0, W1, W2, and a linear combination of xn minus 2. Okay? So, sorry, this is n plus 2. xn plus 1. This is xn. Okay? x of n minus 1, x of n minus 2. Okay? So if I write the convolution of this, so let me write d of n, d head of n is equal to w of n convolution with x of n. So how can I write this one? Now, exactly like this. So this starts from minus 2 to 2 because of this. So this is minus 2, minus 1. Okay. So I have wk. So this is xn minus k. So this is our convolution relation. This is the filtering. So let's check. W minus 2 is multiplied by xn plus 2. And so on. The last one. W2 is multiplied by xn minus 2. So if I define then my W vector as this, okay, and my x vector as this, let's say x of n is still this for the n sample, then if I define, let me write it on the top, the normal equations for this. So what is the normal equations? Are x times, for this x vector, times w times r dx, okay? So what do I have? For this one, again I have expected value of this vector, n plus 2, x n minus 2, n plus 2, x n minus 2, okay? And over here, I have this time expected value of d of n. So there is nothing new actually. I'm implementing the same thing for the new x vector, okay? Times, so my new x vector is this. So maybe on the right hand side, this is equal to r dx of minus 2, r dx of minus 1, so that's maybe the only change, r dx of 0, r dx of 1, because x of n, x n minus 1, r dx of 2, okay? So what we see is, that is it. And this is the standard Rx matrix that we have, okay? So this is a 5 by 5, you know, Rx matrix, autocorrelation matrix. That is it. So once I get the weights for this, okay, then RD0 is known. RDX for this problem is this. Then you apply this, then you get the least minimum mean square error value if you do this. Okay. So nothing changes. So as you see, by introducing this vector, in this way I can solve the smoothing problem almost like instantaneously. Okay. Very good. So what else? So there is a third, let me erase this. There is a third class. This is the prediction. Prediction operation. So what's prediction? Well, it has two types. Let me say forward prediction. Now the issue is this. Let's say I have this X process. So I have some samples of X. Okay. So this is, let's say, X of n plus 1. Okay. Then this is X of n. This is X of n minus 1, n minus 2, X of n minus 3. Okay. So I have 4 samples. Now the issue is the following. Let me have this. Assume that you know these 3 samples. Sorry, 1, 2, 3, 4. You know these 4 samples. Okay. So let me mark them like this. You know these values. But you haven't seen the n plus first value. Okay. For X of n process. Now, can you predict xn plus 1? Can you make an estimate for xn plus 1? Given the previous 4 samples, okay? Or given the previous p samples. Well, let me write the problem. Okay, x hat n plus 1 is, So how can I write this? Again, let me introduce this W0, W1, W2, W3, x of n plus 1. Okay, let me write them. N plus, is it plus? N minus 1, minus 2, x of n minus 3. So samples in the history are combined. Okay. So I'm combining 3 samples in the history and the current sample to make a prediction for the next sample, as you see, with these weights. So this is exactly the same operation as you see, but what is the difference? So all the difference is my desired D of n process becomes essentially xn plus 1. Okay. So if you set your desired process as xn plus 1, then the estimate of it is this. So your desired process is the next sample of the x process. Okay. So if I consider it like this, then I can again use, where is that one? Our normal equations. One more time. So if I set, so if we set desired process, so this is like a definition, then immediately we have the optimal, equation set for the optimal solution. So this is W vector is equal to R dx. So this is the same Rx vector as you see. Okay. Well, no changes. So how about this one? This one is a little bit different because what was this? This is the expected value of D of n times this vector. But let me write this. Okay, something like that. So what is my D of n right now? D of n is x of n plus 1. Okay. If I have x of n plus 1, then for the real valued processes, so what do I have? I have, there are no conjugates essentially over here. So this becomes Rx of n plus 1. Then this is Rx of I would like to write it like this. 1, 2, 3, and 4. Okay. So what's happening? Again, the first argument and the second argument, but please remember that this is also equal to, for the real valued process, Rx minus 1. So how can I calculate this? This is the first argument. Let's say this is the second argument. First argument minus second argument, I get 1. First argument minus second argument, I get 2, and so on. But this is also Rx minus 1, as you see. Okay. So for the real valued process, you don't have to worry about, these conjugates and so on. So let me erase this part. So let me have an example for this. So this is the end of this, okay? This is the end of this, and of course, if you, solve for linear prediction coefficients, W, from this equation system, so only changes, R dx becomes this. If you solve for linear prediction coefficients, then insert them over here. So this is Rx0 right now, okay? Because desired processes power is xn plus 1, its power is Rx0 minus, I have this, okay? So nothing changes. So with the proper definition of an x vector, I can do smoothing. With the proper definition of the desired vector, I can do predictions, etc. Okay, this is the main message that I would like to give. So what is the example? So let's say that Rx of k is alpha to the power absolute k. Okay. So this is an example from Hayes's textbook. There are some other examples, please also check them. Now what is the question? Find 2-tab, let's say, predictor for xn plus 1. Okay? You know, in the optimal sense, let me write this in the minimum, in the sense of optimal filtering, i.e. minimizing MSE. Okay? So I would like to design a 2-tab filter to do this. So actually that is the only information that I need, because this equation system is totally can be written in terms of Rx. Okay. So what's the solution for this? Now let me write this. X of n plus 1, let me write this explicitly, is equal to W0, W1, x of n minus 1. Okay? Well, these are the weights to predict n plus 1 value, this process sample, from the earlier samples in the history of n plus 1. So what should I do? So should I erase this part? Let me keep this drawing. Let me erase this. Let me erase all of it. Okay. So what should I do? Now this is my x of n vector. So I need this Rx, linear combination coefficients, times Rdx. Okay. So how can I write this one? So this is expected value of x of n minus 1, x of n minus 1, this. So this matrix, W0, W1 is equal to right hand side. Okay. So what is this? I have x squared over here, so this is Rx0. This is Rx1. This is Rx minus 1, but okay, let me write minus 1, it's equal to 1. This is Rx0. Okay. So how about this part? So this is supposed to be Rdx. Okay, let me maybe clear on this. So this is, since we have said this, x of n plus 1 and x of n minus 1. So this is Rx1. n plus 1 minus n, Rx1. The sample difference is 1. This is Rx2. Sample differences n plus 1 and n minus 2, 2 samples. Okay, Rx2. That is it. That is the end of this problem, you may say. Now, let me find this values if I can. So this is equal to 1, because Rx0 is equal to 1. This is alpha. This is also alpha. This is equal to 1. This is alpha. This is alpha square. Okay. So what's the solution of this? Well, if I tell you the solution like that, would you agree? This is equal to 0. W0 is alpha. So this becomes W1 is 0. So if W1 is 0, forget about the second column. Multiply the first column by alpha. So indeed, this is the solution, as you see. Okay. So how can this be? The second coefficient is exactly equal to 0. I'm not making use of this, second sample. Okay. So I'm making use of the last sample to predict n plus first sample. So does this make sense? Well, this should make sense to you. Let me keep this. So let's interpret this result. Okay? So let's see, what kind of process is this? If Rx of k is alpha to the power absolute k. So what kind of process is this? So this is, well, it's an infinite response autocorrelation. So this is not a, it's not a moving average process, definitely, because it's infinite length. Okay? So this is actually an AR1 process that we have previously studied. Okay? This is an AR1 process. Maybe you can remember, if I define my x of n like this, okay, plus w of n. Or let me write v of n, because there are some w's over here. So what is this? This is white noise with variance, I think we are clear, sigma v square. Okay? Then if I have such a system, can I calculate the output autocorrelation? So is this clear? So this is a filtering operation. This is a one-pole filter. So what is the output autocorrelation for this system? So please check, let me see. If you don't remember this, it's a very brief exercise. So this is lecture 25, and there is a timestamp at this minute and this second. There is this derivation. Okay, even though it's very simple derivation, well, it ends up with this. It's like a two-step derivation. It takes a minute or so, but I won't be repeating it. Please look it up. Then Rx of k is, so what's Rx of k? This is, as far as I remember, it's something like this. Okay? Rx of k is something like that. Is this correct? So let me try to find this coefficient. That is the tricky part. I think it is correct. Okay. If you check this lecture, you can see how can I find this, with a very brief operation, very small operation. So what do I have? So my, given autocorrelation sequence is this. So what I see is the following. Now in my system, so the x of n process corresponds to a let's say AR1 process with, let's say, sigma v square, this quantity, is equal to 1 minus alpha square. Am I right? 1 minus alpha square. Because there is this cancellation. If you have this, so this is like AR1. Okay, this is the AR1 process. So if you set this sigma v square according to this, you have exactly this. So this is, now this x of n process is indeed then generated by something like this, with a specific alpha value and sigma v square value. This is Rx of k. So if I know, let's say, this sample, and I'm looking for the next sample. So does this make sense then to implement this filter? Okay. So then let me erase this. Then this Wiener filtering xn plus 1 is equal to w0 times x of n plus w1 times x of n minus 1 is equal to alpha times x of n. Okay? This thing. Because this is equal to 0, this is equal to alpha from this result. Makes a lot of sense, since the process is generated by a similar, let's say, recursion. So this is the generation of that process, as you see. So next sample is nothing but the current sample times alpha plus some noise. But that is the uncorrelated part. So I can never predict this part. Okay. So what is my best guess for this? So you can say that the current sample times alpha is your best guess for that. Well, that is it. So let's also calculate linear MMSE result for this estimator xn plus 1. So how can I calculate this? Well, it is this one. So this linear MMSE is RD0, which is alpha to the power absolute k when k is equal to 0, minus this weight alpha 0 times RDX, right hand side, alpha square. Okay, we can get rid of this part. So we see the following. This is equal to 1. So 1 minus alpha square. Okay. So indeed, this tells us that, this predictor predicts the part of the signal, this part, and then the residual part, of course, this is a subtracted version of this, is nothing but this white noise. Okay. And its variance is 1 minus alpha square. So our prediction error variance is exactly like that, 1 minus alpha square. Okay. That is the best we can do, because this is the way this process is generated. There is nothing else that we can do. Okay. So this is an important actually operation. Let me say some comments on this. Prediction is an important operation since x of n may, let's say x of n plus 1, because we have written it like that, may have some dependency. In general it is dependent, and that is the way we can predict it, on earlier samples. That is actually the correlation of x of n samples. Okay. Now let's note this. So if I define my error like this, this is error, prediction error at x of n plus 1 minus x of this. Okay. This is my estimator. Then we know that so what is linear MMSE? Linear MMSE is doing the following. Maybe you can remember this picture, vector space picture. So I have random variables over here. Okay. So I linearly combine these random variables. This is that space. So this is the vector space. So I get this vector. So this is my prediction, x hat n plus 1. So I can linearly combine them, I get this. So how do I do this combination? So I want to be at the closest distance to xn plus 1. So there is another vector over there. This is not in the span of this. Okay. So the issue is exactly as in deterministic least square problems, we have this orthogonality. Okay. So of course this is in the abstract sense. This is xn plus 1, and this is nothing but this difference. This difference is our E. Okay. n plus 1, I can write this if you wish as a vector. n plus 1 minus this. Or this plus error, I get this true value. Okay. Estimate plus error, I get the true value. But what is important is that error is orthogonal in the least square problems, and similarly in this linear MMSE problems we have again this orthogonality. So what do I mean by orthogonality? Of course the following. Okay, so the orthogonality means expected value of E, this error, is orthogonal to, well, let's say that this predictor is something like this, W transpose times x of n minus 1 up to x of n minus p. Okay, it's using p plus 1 samples in the history. Okay, then, so meaning that this is x of n, this is x of n minus 1, so the last one is over here, let's say x of n minus p. So this is the span of p plus 1, what we call essentially vector space elements vectors, but these are random variables. So orthogonality principle is this, x of n, error is n minus p. So this is equal to 0, all 0, p plus 1 times 1. Okay. So, because this is our inner product definition for the random variables, or this is the orthogonality principle for linear MMSE estimators. In case, this is very important, let's write it. This is the orthogonality principle for linear MMSE estimators. Okay. So orthogonality principle for general minimum mean squared error estimators without this linearity constraint is what? Error is orthogonal to the nonlinear processing of the observations also. Okay, not only linear processing of the observations. Linear processing means error is orthogonal to the whole span of this plane. Okay, span of these vectors. Okay, it's not only that; it's also orthogonal to the nonlinear processing, but this is the simpler version. This is linear MMSE. So what we see is the following. Then the prediction error filter that is, if I define, for example, an E of n, prediction error at time n. So it's this actually, x of n plus 1 minus this W transpose of this x of n vector. Okay, so if you check this vector, now this is nothing but xn plus 1, or let me write this, sorry. 1 w0 minus w1 minus wp times x of n plus 1 x of n. So I'm writing the subtraction in terms of vectors one more time, n minus p. Okay, because minus w is multiplied by this, then 1 times xn plus 1 is this, so I'm doing this subtraction. So what we see is this. Now if I have x of n flowing like this, now I may have a prediction. So let's say this is producing x hat n plus 1, and this is predictor. Okay, and this x n plus 1, if I process this with, let's say, okay, so this is plus, this is minus. So this is then error of this. Then this is x of n minus x hat of n. Okay? And the whole thing becomes from this point to this point. So So this, okay, let me draw it like a box. So this becomes the error, prediction error filter. Okay. So what is important? Well, what is important for this system is, well, you can clearly see the effects of x of n at the output. Okay. But you are predicting all the previous dependency in the last p samples by this predictor. So this is essentially what is called the new information. This is called the innovation. Innovation, the novelty or innovation in x of n. Okay. So all of the predicted part is subtracted, and this is called the innovation filter. Prediction error filter is called the innovation filter also. So it's generating the novelty in the x of n sample. Okay. So why is this important? This is essentially equivalent to some kind of an orthogonalization principle. Now if I have xn plus 1 over here, some part of this xn plus 1 is already contained in the span of this. So the interesting part is maybe this part, E. Okay? So this E is the novelty. So E is orthogonal to the previous, let's say, observations. And this is the new information in the X, this is the new information that is not covered in the span. Okay? So this is the reason that we do this, and this is equivalent of orthogonalization of this vector. Okay? Orthogonalization of this vector, finding the orthogonal component of this vector to this space. Okay? Finding the orthogonal component of this vector, which is orthogonal to this space. Okay? Very good. So I have still kept this because of a reason. Now we have this backwards prediction also. So what's backward prediction? Now the issue is this. I was using the samples in the history to predict xn plus 1. Now I'm using backward prediction. Okay, so I'm using x of n plus 1, x of n plus 2 to predict, let's say, x of n minus 1. So now I have the information about these samples. So I'm predicting, so this is an anti-causal operation. Okay, so I'm predicting this one. So this is the question mark. So I'm trying to predict that. So what's the change? Well, the change is not much. Then x at n minus 1 is equal to, well, w0, w1, w2, a linear combination of x of n, x of n. Okay, so let me call this, in order not to confuse you, alpha, beta, gamma. Okay, wn, this is n, n plus 1, n plus 2. Okay, alpha, beta, gamma is, some numerical values that I would like to set. So if you do this operation, now I want to construct this optimal filter for this. So what is the change? So this is just a scalar. So there is no change again. So this is the Rx matrix. So this is backward prediction. So this is, let's say, this vector. Backward prediction. And I have transpose over here. Now this is Rdx. Okay. So what is D? D is xn minus 1. So the sample difference is again 1. Rx2, Rx3. Okay. So how about this one? This is again the standard Rx matrix that we have. Okay. That is it. So what is interesting is backward prediction weights and forward prediction weights are identical, because this equation system is exactly identical. If you want to predict, let's say, in the forward direction or the backward direction, nothing changes. So how can this be? Well, is this meaningful, first of all? So in a sense that if I go in the future, towards the future, or towards the history, towards the past, the predictor doesn't change, okay? So we have such a result. So what's the meaning of this? So how can I interpret this? So actually the situation is this. Let's say that the optimal coefficient to multiply this one, to predict this one, let's say that this is 1/2, this is 1/4, this is 1/6, this is 1/8. I'm just making this up, okay? Or let me erase this. I have only, let's say, 3 samples in the history. So when you multiply xn by 1/2 plus n minus 1 by 1/4, this one by 1/6, this becomes, let's say, your optimal predictor. Now the optimal predictor for this one, n minus 1, if you write this equation system, the weight will be again 1/2. So this is the nearest one. So the nearest one is again multiplied by the same weight. This one is multiplied by 1/4. This one is multiplied by 1/6. Okay? So in this sense they are equal, and this is the reason that I want to write alpha, beta, gamma. Okay? So the nearest one, they have the same coefficient. The second nearest one to the desired sample, they have the same optimal coefficient, and so on. So how can I, well, this is obvious from this equation system. If you write this equation system, actually we have written it, but how can I see this one maybe, in a different way? Well, let's say that x of n process has, let's say, autocorrelation. Autocorrelation. This is Rx of k. Okay. Let me say assume. Then let me have x of, let's say, reverse. This is x of minus n. Okay. So I'm reversing this x of n process in time. Okay. So if you increment n's over here, you are going towards right. If you increment n those here, you are going towards left. Okay. So this is reversed in time. So plus infinity of this corresponds to minus infinity of that. Okay. That's the same to future and the past. They are just switched. So how about this? So what is the autocorrelation of R, this reverse sequence? So can I calculate this? So this is the sequence reversed in time. So this is reversed sequence. So this is a random process. I'm applying this time reversal. Well, just apply the definition. Rx reversed k is expected value of x reverse n, x reverse n minus k. Okay. Then I have applied this. X of minus n, x of, I have minus n minus k. Okay. That is it. So what is the difference in between samples? Rx of k. Because this is real valued process, it doesn't matter whether this is Rx of plus k or minus k. So the difference is k samples, as you see, because this is minus n plus k. So what do I see? Now if I run this process in the forward time or the backward time, so forward or backward process has the same autocorrelation. So after this observation, maybe we can say that, okay, there is no forward or backward for the process, because once I reverse this, nothing happens. It's exactly the same process from the autocorrelation viewpoint. And this is, as you see, only using Rx values. So it's unaware of whether the process is backward whether the process is reversed or process is forward. Okay, so this is a good observation of that. Of course, you know, that is it essentially. That's all I would like to say. And in some applications this can be useful. So let me write a remark. Okay, so assume that you want to estimate, even though we haven't studied this, autocorrelation matrix. So this is what? Autocorrelation matrix is expected value of x transpose. Okay? So we haven't studied this one, but let's say that I have an estimator like that for the autocorrelation matrix. So I have some observation vectors, something like this. Average of this. So clearly, if you take the expected value of this estimate, then expectation goes in, then this becomes X, you know, R matrix. So this is the unbiased estimate of R. Okay. Now here's the issue. This looks like a very good idea, but how about this? I have another estimator. This reversal, it looks like a trivial thing, but so let's say this is like a double hat, double, you know, something like that. So if I do this, x of n, k 1 to n, or x of this, x of k transpose plus x of k reverse x of k reverse transpose. Okay. So if I have something like that, then what happens? If I reverse my vectors. Okay. So what kind of operation is this? Well, this tells us the following. If our matrices, this matrices, let me say, is, what kind of symmetry is this? Satisfies is turtlets and let's say symmetric, i.e. corresponds to an autocorrelation matrix of a Y-sense stationary process. So what's the meaning of this? Then this is something like this, Rx0, I have Rx0 over here, Rx minus 1, let's say, Rx1. But on this diagonal, again, I have Rx minus 1s. On this diagonal, I have Rx1s. So on this diagonal, let's say Rxp, I have Rx of minus p. Okay. Now, if I have such a matrix, R is a totally symmetric matrix, then what happens? Now, if this matrix is, so this is my R matrix, then number one, then let me write this, J times R times J transpose is equal to this R matrix. Okay. So what is this J? J matrix is this matrix, 1, 1. I have ones and zeros. So this is a reversal matrix, as you see. Okay? So you see that this is equal to J transpose. Because it's like a, if you take the transpose of this, you have the same matrix. Okay? Now, how can I see this? This is maybe a little difficult to see, but if I multiply from this J matrix, if I put it on the left, then the first row, if I do this J times R, the first row of this multiplication will be the last row. Okay? So if I do this, I am putting these rows in the opposite order. Last row becomes the first row, and so on and so on. So if I do this J times R operation, so this becomes your first row, this becomes your second row, this becomes your last row. Okay? So this one is moved to the top. Then if you multiply from left, then the first column and last column are exchange. So this one, let me keep track of this. So this one, after this operation, first it moves up, then it moves over here. So it's interchanged by this. But Rx of P and minus P, they are the same. So that is the reason that we have this equality. Okay. Similarly, this one will be moving up, then it will be moving over here after this operation. Okay, is this expected? It's a little bit expected because, since x of n is, samples vector, contains vectors, x of n vector contains samples of a Weissan stationary process. Okay, its reversed vector has the same autocorrelation. We have just seen this. So if I write my reverse vector like this, upside down of x, so this is the reverse vector. Reverse vector. Just we have seen this. We have said that if I have a Weissan stationary process, if I reverse in time, I get, the same autocorrelation. So this is the same fact. Now you have a finite dimensional vector, but you are reversing it. Then of course you have the same autocorrelation. Well, we have also seen this like that because, J times Rx times. So what is expected value of XR transpose? Okay, so this is nothing but J times Rx times J transpose, isn't it? Well, it's exactly this. So we have seen this before, and we have seen it one more time because of this Toepler structure. Okay. So if you come back to this, so if you know that, this is sample covariance matrix estimation, this part. So you are provided by sample vectors. So this is the outer product of all of these vectors. And if you have, R, let me write it one more time, R single hat, this is actually sample covariance matrix estimator. This is called, with 1 over n factor, sample covariance matrix estimator. Okay, so I have that. But what we see is that if X is a Weissan stationary process, so its flipped up-down version or its time reverse version has the same autocorrelation. Now if you flip your vectors, so these are nothing but the kth vector, just the flipped version. Okay, so this is X of R reverse version or flipped version. So if you have a, let's say, n vectors like that, you can double your data set by including the flipped version or reverse version of those vectors, because if X vector contains the samples of a Weisstein stationary process, the flipped vector has also the same autocorrelation matrix. So why not flip them and use 2n vectors in this averaging? Okay. So indeed this can be very useful because you are doubling the number of vectors that you have. Okay. So this can be very important in many applications. Okay, so this is about processes, how we process them in forward time, backward time. So in stochastic processes courses, so I will conclude immediately. This is called reversible. Maybe you can remember from other courses. There is called reversible Markov chains and etc. Okay, this is related with this topic. If you have some earlier knowledge. Of course, this is related with sometimes these chains are reversible, sometimes it's not time reversible, sometimes it is not. Okay, we will continue from this topic later on. Thank you very much.